All right, so NO2 is what we call a free radical, okay? And a free radical is a molecule that has unpaired electrons in it, okay? So it's a molecule with an unpaired electron. In an atomic orbital, okay? So that means we have at least one orbital that's, half filled, right? So we'd have something like that in one of the orbitals. All right. So free radicals are typically unstable, highly reactive molecules because of that unpaired electron. Because electrons, it's energetically favorable for them to be paired up. So they tend to be, highly reactive and unstable. All right. So this is another one of those, molecules, again, that does not follow the octet rule. Okay, so let's look at NO2. So the total number of valence electrons, we've got 5 for nitrogen because it's in group 5, and one nitrogen in the compound. And then oxygen is in group 6, so it has 6 electrons, and there are 2 there. So that's 12 electrons, so we have a total of 17 electrons. All right, nitrogen, okay, is the least electronegative, so that's going to be our central atom. And the oxygens are going to go on either side, okay? So now when we start placing our electrons, okay, we're going to make a single bond to each, okay, and we're going to then place our additional electrons. So we've placed 4 electrons. We've got 4 bonding electrons, which means we've got an odd number of electrons, right, to place in this instance. So let's add electrons to our oxygens so that they all follow the octet rule, okay? And so we've got 6 electrons that we've placed on each, okay? So place 6 electrons on the oxygens, okay? So what that means is, on each oxygen, okay? So that leaves us 1 electron left to place, okay? So we're going to place that on the nitrogen, okay? But you'll notice that the nitrogen is still not following the octet rule, right? So we want to get as close to the octet rule as possible, okay? So we've got all of our electrons placed here, but we don't have nitrogen fulfilling the octet rule. So what we're going to do is what we usually do in these cases, and we're going to take one of those lone pairs, okay, and make it into a bond. So we'll have a double bond to one of the oxygens. Okay, so the oxygens are fulfilling the octet rule. Each of them has 8 electrons around it. The nitrogen now has, 1, 2, 3, 4, 5, 6. It's got 7 electrons around it, okay? So we're not going to exceed the octet rule, but right now we have, we have our nitrogen being electron deficient, okay? So this is the Lewis structure for NO2, okay? And it's, again, you know it's a free radical when you see that one unpaired electron, okay? So, yeah.
So it's better to have a double bond with 7 electrons for the nitrogen than having 5 electrons for the nitrogen for the single bond?
So in terms of why didn't I do 2 double bonds?
In terms of why not just leave it with a single bond?
Why not leave it with the single bonds? So we're going to, what we want to get as close as we can to having 8 electrons on the nitrogen, okay? But the other question that you could ask is, well, why didn't I just, make 2 double bonds to the nitrogen? Then the nitrogen would have 9 electrons, right? And the reason we didn't do that is because nitrogen's in the second row. Right? It's not one of those elements that's phosphorus or beyond so remember that we have some elements that can have more than an octet, those ones that we call expanded valence, but nitrogen can't have an expanded valence. Okay, so there's no probability of electrons being in those expanded valence orbitals. So that's why we go just under the octet instead of just over the octet, okay? And so I'll just make a note of that here. Nitrogen. Yeah.
What are the elements that can be expanded?
So for expanded valence, this is third row and beyond, but we start at phosphorus in the third row, okay? So, and we had a couple of other rules for expanded valence, which, let's see. All right, so let's see, electron deficient. Let's go back here. Expanded valence. Okay, so for expanded valence, it's phosphorus and beyond. Okay. So things that have a higher atomic number than phosphorus. Now remember that we're talking covalent compounds here, so it's going to be nonmetals that are beyond the third row. So things like bromine or selenium, tellurium, polonium, like that, astatine, bismuth. All right, so nitrogen is not an element that can have an expanded valence. So we don't place 2 double bonds. Which would put 9 electrons on the nitrogen, okay? So that's the reason we didn't do that, okay? All right, so again, when we have free radicals, that makes the molecule highly reactive, okay? All right, so let's now talk, we're gonna add one more oxygen to that NO2. All right, so now we have what we call the nitrate anion, okay? So this is NO3 minus, okay? So nitrate is one of our polyatomic ions. So again, the molecule itself has a net negative charge. It's got 1 extra electron. But the atoms are connected by covalent bonds, okay? So it is an ion that's connected by covalent bonds, and that polyatomic ion can form an ionic compound. All right, so let's look at the nitrate anion. So what you'll see up on the screen are 3 equivalent Lewis structures, right? Because we've got a little bit of symmetry. We've got 3 oxygens, okay? The compound itself, when we follow all of our Lewis structure rules, has 1 oxygen that has a double bond to the nitrogen. But as far as the, as far as the atoms are concerned, okay, it doesn't matter which of those 3 oxygens that double bond is to. Okay, so what we have is our double bond doesn't have to be on this one. Okay, so we have equivalent structures that you can draw. So sometimes, many times, okay, there's going to be more than one way you can place the electrons and follow all the rules. Okay, and in that case, okay, what happens is these electrons in that bond right there, that double bond, they don't really always stay between these 2 atoms, okay? These electrons, sometimes they're between these 2 atoms, and sometimes they're between those. And so what we call that phenomenon, okay, is resonance. So the electrons kind of are existing amongst the whole, they can move around through the whole molecule, okay? And so this is a phenomenon that we call resonance, right? Now, what resonance does, okay, is it stabilizes molecules, okay? So it distributes the electron density over the whole molecule, okay, which is kind of a favorable place. So in Gen Chem 2, you talk about thermochemistry, or we might, we might be talking about it at the end of this semester. And we'll talk about things like enthalpy and entropy, okay? So I'm just going to give you a preview of one of the laws of the universe, okay? So one of the laws of the universe is that the universe is constantly evolving towards what some people term disorder, okay? So entropy is this way we have of measuring, okay, the possible ways you can arrange energy in a system, okay? And so higher entropy states are favored because that's the way the universe works, okay? And so when you have electrons, okay, that have, more than one equivalent place that they can be, okay, that is what we would call entropically favorable, and that makes a very stable system because it's the way the universe wants things to move, okay? All right, so molecules like NO3, okay, have this feature called resonance, okay? So let's do an example, okay, of a molecule where we have resonance. And the example that we're going to use, okay, is we're going to look at one example where we have equivalent resonance structures and one where they're non-equivalent. So equivalent means, they're all the same. You can't really distinguish these 3 things, okay? They kind of look, if you turn the molecule around, it would look the same, right? Non-equivalent is when we're going to have a lack of symmetry. So the examples we're going to look at, okay, we're going to look at O3, okay? O3 is a molecule that you've heard of before. It's called ozone, okay? And so let's look at the O3 resonance structures, okay? So what we've got is we can draw it like this, and then we have to put our lone pairs in. So this one is going to have 2 lone pairs. This one will have 1, and this one is going to have 3, okay? So all of our oxygens have the 8 electrons around them, okay? But again, I can also draw it like this, right? okay? So again, because we have, three of the same type of atom, and you can't really distinguish, if you were another molecule that we're going to react with, you can't really distinguish, this from this, okay, when the electrons are in one place versus the other. All right, so now we're going to talk about non-equivalent resonance structures. Okay, so the example that we're going to use for this is another molecule that you've heard of, okay, carbon dioxide, okay. All right, so ozone, okay, is a common name that we use for O3, but if we were going to use our, naming conventions, okay, this is going to would be trioxide, because there's just 3 oxygens in there, okay? All right, so back to CO2. All right, so we could draw carbon dioxide like this. Okay, and this is probably how you're used to seeing it. Okay. But, okay, we could also, okay, draw this. Oops. Does that follow all the rules? Does our carbon have 4 things bonded to it? Do all of our atoms have 8 electrons around them? Does that structure follows the rules? Okay, so this is what I mean by you can draw 2 structures, okay, that both follow the rules in terms of Lewis structures. Okay, so again, both of these molecules have what we call resonance. So in both cases, the electrons are going to be arranging themselves in both ways. Okay? Now, when you have the symmetry that we have here, and you have what we call equivalent Lewis structures, okay, you're going to see this every bit as much as you see that. Okay? So both arrangements of electrons are seen kind of equally. Okay. All right. But in the case of non-equivalent structures, okay, where they are distinctly different, right? And when I say distinctly different, think about the number and type of bonds you have, okay? So a single bond, okay, we have single bonds, double bonds, and triple bonds, right? So in one case, we have 2 double bonds, and in the other case, we have 1 double bond and 1 triple bond, okay? So these are, they're not the same thing, and so in this case, one arrangement will be favored. Okay? So the electrons can move kind of back and forth between. Right? So in an example of this that is something that you could observe, okay, has to do with something you can taste, okay? So does anybody here like honey? I mean, some people love honey, some people hate it. All right, so honey, the main sugar in honey is fructose, okay? And fructose, okay, is a molecule that can undergo isomerization, which is a little bit more than resonance, but it's similar to that, where you get, you can have 2 possible structures for the molecule, okay? And at room temperature, okay, one of those structures is favored, okay? And when you heat the system up, the other structure is favored, okay? And it turns out that the two different structures taste differently to us. One of them tastes sweeter. So if you put tea, or if you put honey in hot tea, okay, that honey is actually going to taste less sweet to you than if you have honey in like iced tea, because it favors the different structure, the different arrangement of electrons. Okay? So it's just an example of how you can sense the difference between resonance structures. Okay. All right. So when there are resonance structures, okay, and this is particularly relevant in biochemistry, okay, we represent the actual state of the electrons by drawing something called a resonance hybrid. So if you'll notice here, okay, we have three possible resonance structures, and we've got our carbonate ion, okay, and so our three possible structures are these. Do these look equivalent to you? So, in this case, again, the only thing that's changing is, who has the negative charge, where your double bond is, but we have symmetry, and so these are all equivalent, okay? And so, in actual fact, okay, the electrons are, sometimes here, sometimes here, and sometimes here. So to reflect that, we draw a hybrid structure, okay, where what we do is instead of giving one of the oxygens, the double bond, what we do is we're going to give, everybody kind of a half bond, and we draw a dotted line to represent the hybrid, okay? Now, we have our negative charges, so we do have to pick, and we do have to, indicate, who's got the negative charge around them, but we show it in the hybrid as everybody has the negative charge sometimes, okay? All right, so what does this mean in terms of the strength of the connections between the atoms, okay? So, if we're talking about connections between atoms, all right, a triple bond is stronger than a double bond. And a double bond is stronger than a single bond. Okay? So, and you can think of it as if, let's go back to our three-legged race. Yeah, Tiff.
I'm kind of confused when bonds
What's
but isn't the bond length also the energy between the bonds, and as the bonds increase, it gets smaller?
Yeah, so we've got two things going on, okay? So, and we're gonna be discussing this more, right? As you have more connections between atoms, so as you have more bonds between two atoms, okay, their connection is going to get stronger, and they're going to get closer to one another. The bond is going to get shorter, okay? And so again, you can think of it as if you're tying two things together, and you've got sort of one loop of a rope, right? And then if you add a second one, right, that's going to make that connection between them stronger. If you add a third one, it's going to make it even stronger, okay? So that's how bonds work. So now let's think about our hybrids, okay? So this is not a double bond, right? The electrons are not always between that carbon and that oxygen, okay? Sometimes they're, here, and sometimes they're here, okay? And so what we would have to say, okay, is this is, a double bond, or it's a single bond plus 1/3 of a bond, right? So 1/3 is like 0.3. So the strength of a bond when there is resonance, okay, is a little bit more than the single bond, and less than a full double bond. So it's actually like a 1.3 bond, okay? And that's going to make a difference in how the molecule behaves, okay? So an example of this, okay, is, let me go to white here so it shows up, is in proteins, okay? So proteins are polymers, so they're molecules where you're connecting monomers up, and the monomers are called amino acids, okay? And the bond that they are connected with is something called a peptide bond. Okay, so this right here, okay, is a peptide bond. It's the thing that connects the parts of a protein together, okay? So this is peptide bond. Now, the thing is, and I won't draw the whole thing out, you can draw a resonance structure for this in which these electrons, okay, go to the connection between the nitrogen and the carbon. Okay, so you have a resonance structure where you can have so I'll just draw the hybrid here, okay? So this is your hybrid resonance structure. And so this bond actually behaves like a 1.5 bond, okay? And what that means for proteins, okay? When you have a single bond, okay, atoms that are kind of attached to the two things that are connected, you can rotate and move around them, okay? When you have a double bond, okay, you're not going to be able to rotate and move around. Okay? So the fact that you have resonance here and that it makes it slightly more than a single bond means that proteins, the shapes that they can take, have restrictions on them because you cannot rotate around that bond. They have lots of other bonds that you can rotate around, okay? But if you've taken a biology class, and you've talked about protein structure and how you have alpha helices and beta sheets and these different kind of regular patterns of structure that you see in proteins. One of the reasons that you see that is because you've got resonance in the peptide bond and you cannot rotate around it. So you'll see these repetitive patterns of structure in proteins because of the constraints due to the resonance of the bonds, okay? All right, so let's forget about biochemistry and go back to general chemistry, okay? All right, so here's just, this is just showing what we drew on the previous slide, which is our equivalent and non-equivalent resonance structures. So the non-equivalent resonance structure that I did not draw on this slide was because it was narrow, right? So this one, I could easily put the triple bond here as opposed to here, okay? So it's just, those are all the possible ways, okay? So that's, again, equivalent versus non-equivalent. All right, did we already? Nope, we didn't do a NO3, right? All right, so let's talk about NO3 minus, okay? And do a quick, let's try to draw all the resonance structures for it, okay? So, N is going to be our central atom, okay? Oops. What's that? Yep. We did do that one? Okay. That was, I thought we did. I just didn't go back enough slides. Oop, there it is. That was our first example, so never mind. I have to get rid of some of my redundant slides. All right. How many? Quick quiz. How many does it have? It's got 3. All right. All right, so that's, whoops. All right, so we've talked about drawing Lewis structures. We've talked about when you have electron deficient, when you have expanded valences, and we've talked about resonance, okay? So the purpose, again, of drawing a Lewis structure for a covalent compound is for us to see where the electrons are spending most of their time, okay, and who's connected to whom, so that we can understand and predict chemical properties, okay? All right, so, and again, you've heard some of these terms already in lab. So, bond order, we've touched on that a little bit. We'll do it a little bit more. So electron pair geometry, okay, shape and molecular polarity, okay, are going to be things that are intimate related to how chemicals act and what they interact with, okay? All right. So, bond order, okay? So bond order is exactly what we said, the number of bonds between 2 atoms, okay? So if there are 3 bonds, the order is 3. If it's 2, it's 2. If it's 1, it's 1, okay? So we've gone through this a little bit before, but we're gonna kind of review. So bond order and how that affects, oops. It's going to affect the length, right, the distance between atoms. It's going to affect something we call the bond energy, okay, which I would call the strength. So we have the length, the strength, okay, and we're going to introduce this term enthalpy, which we use a symbol H to represent, and changes in enthalpy. Okay, anytime you see the Greek letter delta, okay, what it means again is delta is a change between the final state minus the initial state. So if we're doing something like trying to break a bond or to make a bond, let's say we're breaking a bond, okay? Our initial state is the bond is there, and our final state is the bond is broken, okay? So both of those 2 states will have a certain amount of energy associated with them, okay? And when we go from one to the other, we're either going to have to put energy into the system or energy will be given off by the system. Okay, so we're going to start to talk about how energy changes as we change our molecules. Okay. All right. All right. So when we say bond length, okay, it's the distance between our nuclei. Okay, so it's this distance right here, as if we're imagining that the center of the nucleus is a point and how far those 2 atoms are. Okay, bond lengths are experimentally determined. Okay, when we can do things like X-ray diffraction, neutron scattering, where we send very energetic, very small particles or very high energy towards a material, and it scatters off of it, and we do lots of mathematics to analyze, okay, this means this atom was here and this atom was there. Okay, so Our bond lengths are determined by experiment. Does anyone know what we call that? What word we use? When we use an experiment to determine something. Yeah. What's that?
Scientific method.
We use the scientific method. We have two ways that we can come up with a conclusion. We can use experiment or we can use theory. Okay? When we determine something by experiment, we say it's empirically determined. Okay? Yeah. So the term empirical means we played around with the material in the real world, and this is what we figured out from it, okay? And then the other way is we can do things like take the equations of quantum mechanics, okay, and we can use those to answer some question that we want, okay? And that would be answering a question theoretically, okay? Now, the purpose of theory is to both explain and predict experimental empirical results, okay? So the software you use when you use WebMO, okay, that uses, it depending on the method you choose to do the calculation. The ones that you guys used theoretical methods. It used the equations of quantum mechanics, okay? However, there are methods that you could choose that use some of the math, but some of the parameters are empirically determined. For example, things like the size of an atom, okay? That you can, again, measure via experiment, and you can put them in as parameters in your calculation, and it makes that calculation actually go faster when you don't have to calculate everything out. So there's something called semi-empirical methods where you're combining math and experimental results to have your model that then enables you to predict things. Okay. All right. These are experimentally determined. Okay, and it depends on if you have. Let's say I have a carbon-hydrogen bond, and it's in methane. Okay. And then I have a carbon-hydrogen bond, but it's in methanol. Okay, so these differ only by that, that one position, right? So we've got this here, right? Now, if we're thinking about just what's the length of the bond, let's see, the length of this bond. Is going to be very similar, but not the exact same as the length of this bond, okay? Both of them are a bond between carbon and hydrogen, okay? But you have to think of them in terms of the context, okay? So the context for this molecule over here, okay, is that there's an oxygen, and an oxygen has a greater affinity for electrons than carbon does. If we're following our periodic trends, our electron affinity is increasing as we go to the right. So oxygen has more of an affinity for electrons than carbon, okay? So it's going to be, pulling on electrons more. That's gonna affect this carbon that's bonded to this hydrogen here. Okay, so a carbon-hydrogen bond has kind of an average, length, no matter what molecule it's in, but it's going to vary ever so slightly depending on the larger context, depending on exactly what molecule it is. Okay, so the length of this bond is similar to, but not the exact same as this bond. And what I'm going to do is I'm going to move this molecule here just to make it easier to okay? So I'm just going to say context matters here, okay? All right, so you will see tables of bond lengths, and those bond lengths are averages, okay? So let's go to the next page, okay? So again, so we've got two things going on here, right? We have electron affinity, okay? So between the two different atoms in the bond, okay? And we have atomic size, okay? So the greater your electron affinity, the smaller your atom gets, okay? So when you look at this table here, okay, to go back to just what we were talking about on the previous slide, okay? When you see, here is the length of a carbon-hydrogen bond, okay? So this is CH single bond. That's what that position in the table is, okay? Let me just move this so I'm not there. That's an average out of a whole bunch of molecules. Again, so not every carbon-hydrogen bond is going to be exactly 110 picometers. What's a picometer? 1 times 10 to the minus 12th meters, okay? That's pico. So again, these are going to be averages. All right. So as you go left to right on the periodic table, your atoms get smaller. As you go top to bottom, they get larger, right? So bond length is going to increase the bigger your atoms are, right? And you can think of it, just think of the atoms as balls, and think of the distance that they can get to one another. The closest distance is, when the balls collide, right? So you looked at this in terms of energy in lab. So when you did distance versus energy, and this is the coordinate scan you did, right? So I'm just going to say coordinate scan. It's what you did in lab when you did a WebMO exercise, okay? And what you saw, right, is that there's a certain sweet spot where the energy is the lowest, which means it's the most favorable, and this is going to be your ideal bond distance. We'll say ideal bond length, okay? All right. So again, if your hydrogen, okay, is attached to, these are different halogens, right? So in this example, going from left to right is going from top to bottom in the periodic table, right? So this is, oops, let's change that so that we can see it. There we go. And then this one's going to be to the bottom on the periodic table. Oops, I went right off the slide there. Let's do this here. There we go. All right, so as we're going from top to bottom on the periodic table, our halogen is getting larger, okay? And you'll notice our bond distance is getting longer. So the larger your atom, the longer your bond distance. All right, so if you were me, okay, how would you turn that observation into an exam question where you have to apply what you learn? What could I do? I could give you a series of two elements, right? Where, let's just say we have carbon, and then the carbon stays the same, but I have different elements that it's attached to, right? And I could ask you, which one of these has the greatest bond length, okay? And not give you a table of bond lengths, okay? But what information would you have to use to be able to tell me which one has the longest bond? Yeah, Tiff. Periodic table. Exactly. So you've gotten 100% on that exam. There you go. All right. So being able to, again, know your periodic trends, know which atom is going to be bigger than another one, okay? And then saying, oh, the one that's the biggest is going to give me the longest bond because those two balls can't get as close as the smaller balls, okay? All right. So we've discussed this trend, right? Our multiple bonds are going to be shorter than single bonds. Again, so if we just look at a carbon-carbon double bond versus a carbon-carbon triple bond, you see they get shorter, okay? And again, think of every bond as something that's kind of holding and pulling two atoms together, and the more you pull and hold the two atoms together, the more you're going to, the closer they're going to be drawn to one another. And it's all because, okay, you've got electrons, right, in between the two atoms, right? And those electrons are attracted to both nuclei, okay? And the more the electrons that you have in between those two atoms, okay, the greater the nuclei, the greater the attraction of the nuclei are for the electrons that are in that bond. It's going to draw them closer, okay? So that's, again, just going back to Coulomb's law. Now, there's a lot of sophistication that we could get into in the math, but if you can understand Coulomb's law that, the greater the charge you have, the more the force of attraction or repulsion, you can kind of understand what these trends are, right? If I have more electrons in between here, okay, there's going to be greater negative charge to attract both of those nuclei that are positively charged, and they're going to be drawn closer together, okay? All right, so what we're going to do is, to kind of keep us on track, is by the end of today, I'm going to post just like a 15-minute video that I want you to watch before Friday's class. Okay, so, and then because I want to get moving on to Chapter 7 as quickly as we can, okay? All right, so I will see you on Friday. Have a great afternoon.